For the first time since its discovery, the faint trail of 3I Atlas, a possible interstellar object, has vanished from every active telescope feed. Astronomers confirm its signal has dropped below detection thresholds as it slips behind the Sun, entering a 5-week blackout where no one can track its path. That blackout would be routine, except for one detail. Just days before the loss of contact, JPL Horizons quietly revised its orbital solution. The uncertainty region widened, brushing Earth's orbital plane by mid-2026. An impact remains vanishingly unlikely, but the math has shifted. The same models that once placed Atlas near Mars's path now draw the line a little closer to home. The question now isn't whether Atlas is dangerous, it's why the data changed and why it stopped at the exact moment the object disappeared behind the Sun. When it returns, what will it reveal about us, and what we still can't see coming? In late September 2025, just before 3I Atlas slipped behind the Sun, a final set of tracking observations from Mars orbit refined its orbit once more. Using data from the Mars Express and Trace Gas Orbiter imaging campaigns, teams at JPL's Center for Near-Earth Object Studies updated the object's nominal solution, an eccentricity of 1.47, an inclination near 33 degrees, and a perihelion distance of 0.26 astronomical units, roughly 39 million kilometers from the Sun. At perihelion, the modeled velocity approaches 60 kilometers per second, consistent with other confirmed interstellar visitors. Those numbers themselves aren't alarming. What caught analysts' attention was the way the uncertainty region around the orbit widened after the new data were assimilated. The latest Monte Carlo simulations showed one edge of the solution cone brushing Earth's orbital distance in mid-2026, a purely geometric overlap, but one that deserved careful verification. No one inside the community called it an impact scenario, yet its geometry placed Atlas within the neighborhood of Earth's path for the first time. The odds of any intersection remain vanishingly small, but the pattern was enough to prompt fresh calculations. But just as those numbers appeared, the data pipeline froze. Ordinarily, updates to interstellar object ephemerides arrive on a steady cadence through the JPL Horizons database and the Minor Planet Center feed. For 3I Atlas, that rhythm abruptly stalled in early October. Public logs show no new observational updates after the Mars-based series, and for several weeks, the file headers in the ESA Planetary Science Archive remained blank. A short delay can be normal. Calibration routines often pause when a target moves into solar conjunction, but a gap of nearly a month with placeholder entries and missing timestamp metadata quickly drew attention from the amateur orbit tracking community. Analysts noted that several expected FITS image sets from Mars Express's high-resolution stereo camera were listed as received but not publicly released. NASA and ESA officials have offered no statement beyond standard notes about data integrity review. That phrasing likely means the frames are being checked for cosmic ray artifacts or attitude control errors before posting, a common but time-consuming step. Still, to outside observers, the silence feels conspicuous. It could be nothing more than reprocessing or an internal handoff delay between missions. Yet the timing is hard to ignore. The blackout began just as new orbital geometry placed Atlas near Earth's future path. Why did the record vanish exactly when the numbers narrowed toward home? To understand the concern, it helps to visualize the orbit itself. 3I on Atlas entered the inner solar system on a steeply inclined track, about 33 degrees relative to the ecliptic, approaching from above the plane where the planets circle the Sun. Its perihelion lies inside Mercury's orbit, after which the object swings back outward on an escape trajectory toward the constellations of Hydra and Centaurus. When plotted in three-dimensional space, the line of nodes, the point where its path crosses the solar system's plane, occurs not far from Earth's orbital distance. As the object recedes in June 2026, that crossing geometry places its outbound leg within roughly 0.02 AU, or about 3 million kilometers, of Earth's orbital radius. That value represents the 1 sigma uncertainty boundary of the most recent solution, not a predicted close approach, but it is tight enough to merit continued observation. Astrodynamicists compare this to the early calculations for 1I Oumuamua, whose initial uncertainty cone once overlapped Earth's orbit before later data ruled out any encounter. The same refinement process is expected here. No official hazard bulletins exist, no alerts have been issued, and all credible models still classify 3I Atlas as a harmless interstellar visitor. Yet geometry alone commands respect. It reminds scientists that precision drifts with distance and that small errors can mimic proximity. Geometry doesn't predict danger, but it doesn't rule it out either. With official data streams slowing, the vacuum fills itself. As 3i Atlas slips behind the sun, astronomy forums and social feeds erupt with competing interpretations of the final orbital updates. Some users claim to see discrepancies between the Minor Planet Center's solutions and the live JPL Horizons outputs. Others argue those differences come from normal rounding of orbital covariance terms. Small mismatches, fractions of an astronomical unit in predicted coordinates, quickly snowball into speculation. Screenshots circulate with captions like "trajectory adjusted again" or "impact corridor extended." In truth, none of the numbers imply any impact risk. They reflect ordinary recalibration as Atlas moves beyond the range of precise tracking. Still, the public tension mirrors earlier episodes like the 2019 chatter around 2i Borisov, when data scarcity invited rumor. Space agencies issue brief reminders that interstellar trajectories are inherently uncertain until reacquisition, but reminders rarely travel as far as speculation. For professionals inside the field, this episode becomes a case study in how a silence of a few weeks can echo louder than any press release. The science hasn't changed, only the narrative has. When numbers stop flowing, imagination fills the gap. Before the data gap in early October, both the Mars Express orbiter and the Trace Gas orbiter captured faint spectral readings of 3i Atlas as it passed near Mars's orbital distance. The provisional analyses showed something unexpected. The dominant emission feature was carbon dioxide, not water vapor. In most comets, water is the primary driver of outgassing as they approach the Sun. Here, however, the H2O signature appeared weak to absent, while CO2 and carbon-bearing molecules were unusually strong. Preliminary comparisons to laboratory reference spectra suggested another anomaly: a higher than expected nickel-to-iron ratio in the metallic emission lines, a pattern more consistent with dense, refractory material than with volatile ices. While calibration uncertainties remain large, the early interpretation pointed toward a dry, massive nucleus, perhaps richer in metal and carbon than typical comets. If that assessment holds, it changes how the object behaves under solar heating. A dense, low-volatility body produces less jetting and less solar pressure variation, which can make its trajectory more stable, yet also harder to correct through outgassing models that rely on visible activity. The physics remain sound, but the implication lingers. Could density itself be what hides its true path? Once the early spectral data were logged, modeling teams began testing how a dry, metal-rich body could behave as it moved through the inner solar system. Engineers at JPL and ESA's planetary dynamics groups used radiation pressure and thermal inertia simulations to see whether a nucleus with low volatile content might subtly alter its course under solar heating. The findings were instructive. A reflective, nickel-bearing surface would absorb and re-radiate energy unevenly, creating what's known as the Yarkovsky effect, a faint thermal thrust that can shift an object's path over months or years. For a kilometer-scale interstellar visitor, the change would be measured in tens of kilometers, not millions, but it complicates any long-term projection. Researchers also compared Atlas's light curve with those of 1i Oumuamua and 2i Borisov. Where Borisov's brightness fluctuated wildly with outgassing, Atlas remained almost flat, implying a slow rotation or an unusually compact shape. Either trait could mask the subtle accelerations used to refine orbital fits. In workshops held in early November, dynamicists described the situation as informationally asymmetric. The object's geometry may be ordinary, yet its physics appear tuned to hide small but significant forces. None of this implies control or intent. It highlights how incomplete data can exaggerate the illusion of mystery. Still, as the simulations ran, one realization unified the teams. Even when the numbers fit, the models remain only approximations of an object that has never been seen up close. Sometimes the hardest thing to predict is the absence of behavior itself. To illustrate the scale, not the threat, researchers have modeled what would happen if a body with Atlas's estimated mass and speed passed near Earth's orbit. Based on its apparent brightness and likely reflectivity, its nucleus might span 1 to 2 kilometers, giving a mass on the order of 10 billion tons. Traveling at 60 kilometers per second, its kinetic energy would approach 10 to 24 joules, equivalent to tens of millions of megatons of TNT. That number is purely theoretical, describing total motion energy, not a forecasted impact. Even a distant flyby at that velocity would have visible effects: ionization of dust, a faint plasma sheath, and, if it intersected the upper atmosphere, a brief but brilliant vaporization trail. Earth's atmosphere would shield the surface from all but the most massive fragments, yet the radiant energy released overhead would surpass any human-made explosion. These exercises exist to bound extremes, not to predict them. They help mission planners test detection systems and energy dissipation models for potential future interstellar encounters. So far, every credible analysis keeps 3I Atlas on a safe, outbound path once it clears the sun. The object remains real, its energy undeniable, and its trajectory still under refinement. The math is cold, but the margin of error is human. As October gives way to November, the Global Watch Network turns its attention to December 2025, when 3I Atlas is expected to emerge from solar conjunction. Amateur astronomers, university observatories, and agency telescopes begin coordinating to reacquire the faint interstellar visitor. The Pan-STARRS survey in Hawaii, which first alerted researchers to 3I Atlas months earlier, schedules a follow-up campaign. The Vera Rubin Observatory in Chile, still in early operations, prepares to allocate a short observational window during its all-sky cadence. Even the European Space Agency's Gaia mission includes Atlas in its December target list to refine its position by parallax. Models suggest that between December 9 and 15, the object should brighten just enough to reappear in the morning sky. Each missed day of observation after that window doubles the positional uncertainty, expanding its predicted corridor across millions of kilometers. For professionals, reacquisition is a matter of precision and patience. For the public, it becomes a test of trust. Social feeds speculate, countdown clocks appear, and live streams promise to catch Atlas, live. But space doesn't work on human timelines. The object will appear, or it won't, on its own schedule. Every hour of silence pushes the corridor closer to guesswork. Inside space agency offices, caution takes priority over speed. Any update about a potential near-planetary encounter must pass through layers of verification, ephemeris checks, peer review, and cross-agency sign-off before public release. For 3I Atlas, that process has been deliberately slow. The Minor Planet Center's listing for the object has remained unchanged since early October, showing the same orbital solution used before conjunction. There is no hidden warning or classified alert. The freeze reflects procedure. Agencies avoid premature statements that could trigger unwarranted alarm or erode confidence if later corrections prove the data routine. Review boards inside NASA and the ESA evaluate each revision not only for mathematical accuracy, but for communication impact. The line between transparency and overstatement is thin, and officials know how quickly speculation outpaces evidence once a story escapes the lab. The silence, therefore, serves two purposes: ensuring credibility and preventing the narrative from running ahead of the numbers. Still, for anyone outside those review rooms, the quiet feels heavy. Information delay is indistinguishable from secrecy. Who decides when a risk is real enough to share? Months of tracking have led to a paradox: an interstellar object observed, analyzed, and then swallowed by the sun's glare. What began as an anomaly, a shifting orbit, incomplete spectra, a silence in the data streams, has become a mirror of how fragile certainty can be in the space between. Here's what is known. 3I Atlas follows a confirmed interstellar trajectory. Its orbital uncertainty is small but non-zero, its composition atypical yet still natural, and no credible model predicts an Earth impact. The science stands on stable ground. What remains open is measurement. Reacquisition imaging, updated spectra, and refined trajectory fits once new data arrive. Until those numbers return, hypotheses multiply. Was the widening uncertainty cone a simple artifact of missing data? Could the metallic composition alter its radiation pressure and motion ever so slightly? Every theory waits for one more observation to survive. By mid-December, telescopes across 3 continents will aim at the pre-dawn sky, searching for the faint streak that will end the blackout. When it returns, its brightness and position will settle months of speculation in a single frame. When 3I Atlas reappears from the sun's glare, the data will tell one truth: whether we imagined the threat or simply glimpsed the unknown moving through our solar system's light.